A very good morning to my respective chair and the audience. Today I'm going to present one of my research, structural exploration through cations distribution of Al3 dope nickel zinc cobalt ferrites. Introduction. Ferrites have unique chemical compositions and crystal structures. They have electric and magnetic properties. They have versatile applications like magnetic switches, magnetic storage, gas sensors, etc. Nickel zinc ferrites have unique crystallographic lattice sites with ionic radii, particle size, grain structure, and cation distribution. Introducing cobalt may significantly enhance nickel zinc ferrites' magnetic characteristics. Nickel zinc cobalt ferrites can alter themselves to work effectively for the devices that functions above 1 MHz like microwave absorber, EMI shielding, etc. Aluminium doped in nickel cobalt ferrites control over their electric and magnetic properties, and that make them suitable for the applications like telecommunication, power transformer core, etc. Aluminium substituted nickel zinc cobalt compositions still remain unexplored. Enhanced magnetization expected to be found after L doping in nickel zinc cobalt bulk ferrites. Assume that it works effectively for high frequency devices. Materials and method. This is the flowchart we see here. Actually, we synthesized all the bulk ferrites through conventional ceramic technique, and here is the flowchart. Characterization techniques. To characterize the ferrites, we use several techniques. At first, we used XRD for at first we use the X-ray diffractometer, and through that diffractometer we confirm that all the crystal structure is formed for all the ferrites. The Raman spectroscopy confirmed that the metal oxygen bonding is present inside the structure. The high revelation field emission scanning electron microscope FESM display the microstructure present inside the materials. Mossberg spectroscopy give the environment, magnetic environment which is present inside the material. The PPMS measure the MH loop and the magnetic properties inside the material. Results and discussion. X-ray diffraction analysis. The XRD refraction peaks from the planes 111, 220, 311, 222, 400, 422, 511, 440, 5620, 533 confirm that the formation of single phase cubic spinel structure with phase group FD3M, the lattice parameters are estimated both experimentally and the Rietville refinement method. And here we see the lattice constants are showing a declining trend with the compositions. This is the crystal structure for all the compositions. The lattice constant is showing a declining trend with the compositions, and that is 8.3859 angstrom to 8.3745 angstrom. Actually, when less ionic radius Al3 plus force larger ionic radius Fe3 plus in B site to redistribute in A site, because the less ionic radius replace the larger ionic radius. As a result, the unit cell is compressed and the lattice constant is showing a declining trend with the composition. Here we see that after doping, the cations are redistributed inside the voids, and this is the cation distribution inside the voids. And also we see that Our oxygen position parameters is varied with compositions because when the cations are redistributed inside the voids, the oxygen position parameters or ionic parameters are changing their position to feed the cations inside the voids. As a result, the oxygen position parameters are varied with compositions. Microstructure exploration. Here we see how the grains are redistributed inside the compositions, and we see that the grains are irregular in shape and enclosed with grain boundaries. And here we see that our grain size is showing a declining trend with the compositions. Actually, after Al doping, a thin layer of oxygen aluminum is formed around the grains and hindered the grain growth. As a result, the grains are showing a declining trend with the compositions. This is stem analysis, and this microstructures is for the compositions where aluminum content is 12%. And here we again see all the grains are irregular in shape. This is high resolution transmission electron microscopy HRTEM image, and we see that the lattice planes are equally distributed, and that indicate that the lattice are free from defect. And this is shape pattern, selected area electron diffraction pattern, and this circular pattern indicate that the strong crystallinity is present inside the materials, and the planes which is obtained through that diffraction pattern is exactly matched with the plane which is obtained through the XRD data. So we conclude that the strong crystalline is formed for all the compositions. Raman spectra studies. Here we see that the A1G1 modes, this is found in the range 625 to 665 centimeter inverse. This is symmetric stretching vibration of metal oxygen bonds that is present in A site. And also we see that a extra peak for the compositions with x equal to 0.12, and this indicate that the aluminium resides in A site, and this extra peak indicate the aluminium oxygen bonding in A site. Here, A1G1 mode is obtained around, say, 700 centimeter inverse. This is symmetric stretching vibration for iron oxygen bonds in A site. T2G mode represents the asymmetric stretching of metal oxygen bonding in B site, and this is found around 346 to 465 centimeter inverse. T2G3 modes represents the asymmetry bending between iron and oxygen or other cations and oxygen in the B site, and this is found around 508 to 566 centimeter inverse. EG mode represents symmetric bending of oxygen anions and metal cations in A site, and this is found 262 to 337 centimeter inverse. T2G mode obtain 196 to 238 centimeter inverse, and this is represent the translational motion of the whole tetron for the bulk ferrites. Actually, the AO4 group is represent the vibrational modes above 600 centimeter inverse, and this is obtained for tetrahedral site or for A site. For octahedral site or for B site, this group is indicated through BO6 group, and the vibrational mode is obtained below 600 centimeter inverse. When aluminium is doped inside the material, instabilities occur because electron hopping is generate between the cations and anions inside the material, and due to this instability, the cations are rearranged themselves until the stabilities occur. That is the reason why the metal oxygen bonding is slightly shifted or reshifted from one composition to another. Mossbeer spectrostudies. 57 iron Mossbeer spectroscopy investigate the magnetic environment around the iron cations. The two G-man splitting sectors indicates the contribution of ions in the voids or A site or B site. The iron's occupancy in the A site and B site is obtained through the formula, and here we see the iron occupancy is 25.5% for A site and 74.5% for B site for the composition with X equal to 0. 33.3% for in A site and 66.67% in B site for 2% aluminum content, 34.87 for A site and 65.13 for B site for the composition with X equal to 0.05. The ferrite with aluminum content 7% have the iron content, iron area that occupied the A site is 29.50% and 70.4% in B site. 35.79% for A site and 64.21% for B site for the composition with 10% aluminum content. And at last, but not the least, 32.45% for A site and 66.55% for B site for the aluminum content 12%. Here we see that the isomer shift ranges between 0.278 millimeter per second to 0.44 millimeter per second, and that indicate that all the samples have Fe3 plus high state. The low values of quadruple shifting indicates that the magnetic faces of the voids are almost close to cubic symmetry. The hyperfine field indicates magnetic dilution inside the sublattices. Line width with Al contents provided evidence of cation rearrangement inside the voids. The magnetic properties analysis. Here we see the saturation magnetization is showing a declining trend for the composition, declining trend 82.221 EMU per gram to 70.14 EMU per gram for the composition with X equal to 0 to X equal to 0.02 samples. And then the magnetic saturation increases from 75.91 EMU per gram to 93.03 EMU per gram for the compositions with X equal to 0.1 to X equal to 0.12 samples. Actually, when aluminum is doped inside the material, the cations redistribute inside. As a result, the magnetic super exchange strength inside the voids are varied, and when the super exchange interaction varied, the magnetic saturation is also varied. So we conclude that the cation distributions, super exchange interaction depends on cation distributions, and the magnetic saturation depends on the super exchange strength inside the material. As a result, the saturation magnetization varied with the compositions. And here also we see the composition with 12-pi aluminum content show the highest saturation magnetization, and this is 93.06 EMU per gram. Because some of the aluminum resides inside the A site in 1:2 ratio. Due to that reason, the net magnetic moment is reduced, and as net magnetic moment is increased, as a result, the saturation magnetization is showing the highest value for the sample with aluminum content 12%. And this assumption is also confirmed through the Raman data. Conclusion. Throughout the studies, it was confirmed that the bulk ferrites structure was formed for all the compositions. Enhanced saturation magnetization is obtained, and this enhanced saturation magnetization indicate that the bulk ferrites may function effectively for multi-phases electronic devices in high frequency ranges. Thank you very much.